Today, you're going to get your calculator back in a minute. So when we are taking square roots or cubed roots, we need to remember to keep those decimals to having the same number of places today to make the comparison. That'll be the only challenge when we are comparing real numbers using the calculator. But before we get there, we need to talk about, I kind of glossed over this last time, knowing this lesson was coming, but what is a real number? So we're going to start by classifying real numbers. Just it's vocabulary. And it's really a matter of knowing the names, just like you would understand the definition for a word. So we're going to walk through the number groups, which you've already done up to rational numbers. We've added a new group in 8th grade, so we will talk about that. So part of this should be a review, but again, it's just knowing the vocabulary, everyone. Now, this is in your book on page 90. Up to 7th grade, we worked with rational numbers, which I'm going to explain again what that is. We have just added a new group with our roots called irrational numbers. And when we combine those two groups together, it becomes the real number. So 7th grade kind of topped out at rational numbers. 8th grade, by adding all of these ideas of roots, is kind of top out at what's called a real number. Now, your book has this diagram. I don't know if you remember that this is called a Venn diagram. And it has a circle inside of a circle, kind of inside of the oval inside of the box. And as the group goes up, all of these numbers in the middle circle are also part of the bigger rectangle here, okay? I'm going to walk through this in a different way in a second, but what I'm about to do is all shown in this one picture. So we're going to start in the center in the green circle, and these are called the natural numbers. So I'm going to walk through this kind of one step at a time, kind of building this chart in a different way. So we're going to start with the natural numbers. Those are the numbers that you first learned as a little preschooler. You went around counting everything. You would count books, you would count leaves, everything, and you always started with 1. So it would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Those are the numbers that we use to count. They used to be called the counting numbers, but now they're called the natural numbers, and that's your first number set. So the number 1 is a natural number. The number 10 is a natural number. The number 3.5 is not. Okay, you don't count 3.5 leaves, okay? So natural numbers 1, 2, 3, 4. When you got into kindergarten, a new number and only one number joined the group, and it was the number 0. In kindergarten, I remember my kids calling him Zero the hero, right? So you came up with the idea that there was something that represented nothing. So if you add 0 to the whole numbers, to the natural numbers, this is now called the whole numbers. And I like to tell people, think of 0 as the whole of a donut. So one single number came into the group, and it's a whole number. So 3 is a natural number and a whole number. 4 is a natural number and a whole number, but 0 is only a whole number. It's not considered a natural number. So as we go up, each group becomes part of the group above, but not the other way around. Somewhere towards the end of elementary school, you started to think about the fact that the whole numbers had opposites. The negative whole numbers, like -1, -2, -3, -4. Temperature was an area that we talked about when we first introduced those negative numbers. Those are called the integers. So if you take the whole numbers, which are the 0, 1, 2, 3, 4, and you add all of their opposites, that would be the integers. So the number 1 is a natural number. It's a whole number. It's also an integer. The number -1 is an integer, but it's not a whole number or natural number. So again, as we go up, each group becomes part of the next group, but not the other way around. Now notice what's missing in here. We don't have 2.5. We don't have -4.7. So we haven't quite brought in those decimals and fractions. That's the next group. So if we add terminating decimals, which you and I talked about at the beginning of the year, they're decimals that end 0.45, stop. Negative 0.243, stop, right? Terminating decimals, end. We also talked about repeating decimals using bar notation, or you would kind of use this dot, 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 but this would be negative 0.33333333333, and keep going. This would be 0.23232323. Those are repeating. And also our fractions like 1/2, or mixed numbers like -2 3/5. All of these numbers are now coming in, and they're called the rational numbers. So you might stop and say, what's missing? Isn't that everybody? Well, we have added another group, which is called the irrational numbers. I like to call them the weirdos. Don't mean to make fun of them, but they are this sort of the strangest numbers we've encountered. So something like the square root of 3. Remember, if you put that in the calculator, it goes on and doesn't repeat and doesn't end. Well, in the calculator, it looks like it ends, but it would keep going. I mean, in our classroom, we have pi hanging over the windows. Same idea. So the irrational numbers are, represented by decimals that never end and never repeat. Up to this point in time, you only viewed pi, but now if you take a square root of any non-perfect square in between those numbers on the perfect square trail, it is an irrational number. So this is kind of what's come in pretty heavily now in 8th grade. 7th grade kind of ended over on the rational numbers. If we put the rational and the irrational together, that is where 8th grade tops out, calling the real numbers. Now, what I need you to know is that real numbers are either rational or irrational. They cannot be both. So you cannot have a number that's both. Now, you can have a number that is an integer and a rational number. These numbers, right, become part of this group, become part of this group, become part of this group, become part of this group. But when we're over here, irrational are only part of the irrational and real. Now, just before we go on, that's where we're going to stop, but I just want to add a thought for the future. We talked a little bit about if you try to take like a square root of -1, the calculator blows up with an error. And I said somewhere down the road, you'll talk more about this. There is something called, another number group called the imaginary numbers. They are those even roots of negative numbers, and you'll talk more about that. You do not have to worry about this right now. I'm just letting you know that we're not done. There's going to be more interesting things coming down the road. So basically in your book on page 90, the first part of today's lesson is, can you just tell what groups these numbers belong to? So name all sets of numbers to which the real number belongs. So 0.25, 25, 25, 25, 25, that is a repeating decimal. So if I go back and I look right here, repeating decimals would be a rational number. So he starts here in this group, and then he belongs to any group above. So the rational numbers and the real numbers, rational and real. So 0.25, 25, 25, 25 would be considered rational, and the group above, which is reals. Now, square root of 36, for a minute there, you see that square root and you want to jump into the weirdos, into the irrational, but it's kind of like wearing a Halloween mask, because that is a perfect square. So the square root of 36, and again, we're just looking at the principal root here, the positive root, is 6. And once you see that this is just a mask for the number 6, we're going to go back. So where does the number 6 start with? It's a natural number. When you were a little 3-year-old, you counted 6 leaves, for instance. So 6 would be a square root of 36, which is 6, would be a natural number, and a whole number, and an integer, and a rational, and a real. He has all kinds of groups that he's part of, and here they all are. I'm listing them in a better way than your book, so if you're on page 90, you might want to add this to your book. And don't forget, you can always pause the video to do that. Now, the square root is 7. If we look at the perfect square trail on our multiplication chart, he is not circled. He's not a perfect square. So if we did put him in the calculator, you're going to see something like this, and it happens to be negative as well. They're looking for the negative root. It never repeats. It never terminates. So don't forget, that's the group over to the right here called the irrational numbers that I affectionately called the weirdos. So that is an irrational, and the group above, which is real. And that's how we classify numbers. So I'm going to have you do the same thing here with 3. They are on page, whoops, I went buzzing by, page 90. So if you could pause the video and try to name all the number groups that these belong to. Okay, so the square root of 10 is not a perfect square. So he is going to have a decimal that does not terminate and does not repeat. It's going to be irrational, and the group above is real. Ooh, here is a mixed number, a fraction. If you look back at our table, he is part of the rationals, and up above that is the reals. Now, you've got to be careful here. You're almost tempted to say the same thing you did on A, but the square root of 100 is kind of like a Halloween mask. Behind that is the number 10. Again, looking just at the principal root. And 10 goes all the way to the bottom of the chart, so it is a natural number. It is a whole number. It is an integer. Keep going. It's a rational, and it's a real. So he's a pretty popular number, the square root of 100. He belongs to all these groups. And that is classifying real numbers. We did this in 7th grade, but we stopped at the rational. We didn't have these 2 words, irrational and real. So before we go any further, you need a scientific calculator. So you don't want just a basic calculator. It needs to have a square root and a multiple root button. I'm going to show you how to use a square root right now. And when we have our live meet, I will show you how to use a cube root. I'm just separating those 2 ideas to sort of not have a mix-up in your head, okay? So I am going to use the TI-30 calculator. We can, in class kind of figure out where the buttons are on other calculators, but they're relatively the same from calculator to calculator. So I'm going to find the square root of 30. Now, what I always recommend is before you head to a calculator, have an idea in your head what it should be. These devices are great until you hit the wrong buttons. So if you have an idea about what this should be, if you get something weird on the calculator, you kind of know you made a mistake. So just remember that the square root of 30 has to be bigger than the square root of 25, has to be smaller than the square root of 6, right? 36, 6. So this has got to be 5 point something. If all of a sudden you got 12.37 on the calculator, oops. So my recommendation is always to give it a quick estimate right now. We know it has to be in between 5 and 6, okay? So now here's the buttons that you're going to push on the calculator to find the square root of 30. So the first thing on this calculator and most calculators is there's a second button. In this case, it's blue. So that puts you into the blue function. So you're no longer looking at the writing on the buttons, you're looking at the blue writing above, okay? So you're going to hit that second, and then you're looking for the square root symbol in blue, which you'll see is right above that x squared. Well, think about it. They're opposite operations. So the calculator very smartly put them sort of on the same button. So you hit the blue, and then you hit this x squared, which should put a square root symbol on the calculator. And then you are going to type your 30 and hit equals. So you're going to hit the second, then this x squared button, which will give you the square root, type in whatever number you want and hit equals. And on the calculator, you should see 5.4772255575. It is an irrational number. It does not repeat. And I know it looks like it terminates, but remember the calculator is only so big. So if you used your phone or a calculator that is bigger, you'd see more places. So the square root of 30 is about 5.4772255575. And we thought it was going to be in between 5 and 6. So we're feeling relatively sure of how we worked with the calculator. Okay, so that's how you find square roots. Let's use that moving forward. So on page 91, this looks like a problem we just did the other day, but I'm now giving you the calculator because these are too close to call. To estimate, it's kind of tight. So I'm going to put the square root of 7 in the calculator, and the display is going to say 2.645751311, right? And I'm putting the approximation because we haven't ended. It keeps going. 2 2/3. Now, you can remember that 2/3 is 0.6 repeating, or don't forget, if it's in front of the fraction, it's in front of the decimal, and 2 divided by 3 is going to give you 0.6666666. So what I said at the beginning is you've got to look at the same number of places. So there's the 2, and those match. And when you get to the hundreds place here, you now can see who is bigger. So the 6 is bigger than the 4. The alligator is going to eat the bigger number. So the symbol should be less than. The open mouth is opening up to the 2 2/3. So the square root of 7 is less than 2 2/3. How are we getting these values? How are the book getting those? They're using the calculator. So now I have 15.7%, which, remember, you take the percent off and move that decimal 2 places smaller. So that's 0.157. And then I'm going to take my calculator and I'm going to take the square root of 0.02. And you've got to hold out a number of places so you can see, like up here, if you had only put 2.6 and 2.6, you couldn't see who's bigger, right? So the square is 0.141 already. I know that the 15.7% is greater. So then I'm going to have 15.7% is greater than the square root of 0.02. And the book's doing a nice job of just showing you that on the number line, reminding you that if a number is plotted to the left on the smaller side would be to the left of the other number. So left to right is going least to greatest. Okay, so your turn on page 91. I'm going to ask you to pause the video. You're going to use your calculator if you need to in life. Basically, remember you can do that now. And remember to hold out the number of places so that you can make an accurate comparison. And when you're set, come back and let's see how you did. Okay, the square root of 11 in the calculator is 3.3166. And 3 1/3 is 3.333. See, so as soon as I look, there are 3 matches in the front. The tens place matches, but the hundreds place, this guy is bigger. So I need to make sure that the alligator eats the 3 1/3. So the square root of 11 is less than 3 1/3. That's not too tough, is it? Again, I'm allowing you to use the calculator. I know that the square root of 16 is 4, and this is a little bigger than 4, but see, now it's too close to call. I'm not sure. So I'm going to use the calculator to get a more precise number, and the square root of 17 in the calculator is 4.123, and now I can make this comparison. So if I look, the 4s are the same, but look at the tens place, the square root of 17 is bigger. So the square root of 17 would be greater than 4.03. So now I'm going to, 250%, just take the percent sign off and move that decimal 2 places in. So this guy would be 2.50. When I take the square root of 6.25 in the calculator, this one you could have actually used your square root trail because he's a perfect square with that decimal. We talked about putting that back in. But you can use the calculator, and you should have actually seen that in this particular case, they came out to be equal, 2.50, 2.50. By the way, if you have a terminating decimal, a decimal that ends, if you need to add more numbers on the back of it to make a comparison, it would be zeros. The only time you would add 5s here is if there was bar notation. So once a decimal terminates, what happens after that would be zeros. So here is ordering a set from least to greatest. And again, I would be taking out my calculator and figuring out what some of these were, and then we'll make the comparison. Now I'm going to caution you. Notice they're negatives, and negatives go in the opposite direction, and we want to go least to greatest. Pause the video, get your numbers here all in decimal, figure out the order. We're going to plot them, and then we'll rewrite these 4 numbers in order least to greatest. Okay, so I would have started kind of down here. Well, -7 is -7. And notice I just put some zeros on there. Negative square root of 60 is -7.74596, and I stopped. -7 7/10 would be -7.7, and I'm adding some zeros on after that so I can make a comparison to the number above. And 66 divided by 9 would be -7.33333. So now I need to remember that when I go least to greatest, right, negatives go in the opposite direction. So I'm going to show you kind of where they plot up here. So this -7.7-ish is where the green dot is. The -7.745, the square root of 60 is where the blue dot is. The -7 7/10 is the -7.7. The negative 7.3 repeating is right about where the purple dot is, and obviously negative 7 is there. And what you need to notice is that this negative 7.74596 is actually smaller. The negatives go in the opposite direction. So if we were going to order these guys, the first one should be that negative square root of 60, then the negative 7 and 7/10, then the negative 66 divided by 9, and then the negative 7. And we write them in the original forms they were given. So just be careful. I wanted to do a negative one to remind you that the negatives go in the opposite direction. So finally, where the heck is this stuff used? So one of the places that square roots are used is your sight line to the horizon, being how far can you see, out towards the horizon. So on a clear day, the number of miles a person can see to the horizon is about 1.23 times the square root of his or her distance from the ground in feet. So the higher you go up, the further you can see towards the horizon. I mean, that makes sense. And they've figured out that this little formula here, 1.23 times the square root of how high you are off the ground in feet, will tell you how far you can see, given that it's not a stormy day. So suppose Frida is at the Empire State Building observation deck in New York City, and she's 1,250 feet up. And Kaya is at the Freedom Tower observation deck, and she's a little bit higher, 1,362. How much farther than Kaya see than Frida? So we got to find out, first of all, how far can they both see? So you're going to take 1.23 times the square root of their height, which for Frida was 1,250. I'm going to take out my calculator. Square root of 1,250 times 1.23. She can see about 43.49 miles. Kaya, who is further up, when I do the same math, 1.23 times the square root of her height off the ground, can see a little bit further. How much further? When you hear that how much further here, we're going to take the bigger minus the smaller. So Kaya, by going up that extra little bit, can see almost 2 miles farther, 1.9. So this is just an example of one of the places that square roots are used. At some point, we'll talk about the fact that also when you have a skid mark in a car, that also involves a square root that can kind of tell you how fast you were going, which is pretty cool. So today I'm hoping you're going to remember your number groups so you can classify a number as to what groups it belongs to. And the second thing would be to be using the calculator to take square roots and make comparisons. We will talk about how to do the cube roots, but we'll do that in our live meet. Okay, everybody, have a great day.